So here's the agenda, three parts. We'll start by talking about high-risk AI systems. In the beginning, traditional software versus AI software, AI models, generative AI foundation models, large language models, AI agents, development of AI software, and deployment of AI software. And then we'll talk about four use cases: Google Vertex AI, which I use, Gemini, which is part of Google Vertex, Open Evidence Medical Information, which my son uses. My son is a doctor and he uses Open Evidence Medical Information. We're going to talk about agents as well, multi-agent booking system and Oracle Fusion, HCM, Benefits Advisor, which is Oracle's human capital management system. And specifically, they use agents for managing their benefits, their health benefits. The key takeaway is how AI systems work, architecture and workflow, how AI systems are implemented, public cloud, private cloud, etc. Part two are threats, vulnerabilities, and security controls. Threats are adversarial AI attacks. Vulnerabilities are based on the OWASP Top 10, Vulnerabilities for LLM Applications 2025, which was published last March. So I'm assuming that the 2026 version will be published this coming March. And then some of the AI control frameworks, there are many of those, but the three that I'm going to cover are NIST ASP 800-218A, which is looking at AI controls in development. The Google Secure AI Framework, which looks at AI controls in both development and deployment. And the OWASP AI security controls, which again looks at security controls in both development and deployment. And a key takeaway is the current view of threats, vulnerabilities, security controls, but there, as I mentioned, there are several other controls frameworks currently under development and recently being deployed, including the NIST cybersecurity framework for AI, which was just published in December of 2025. And the Cloud Security Alliance, the AI controls matrix, which I include in my full day class. And then finally, let's get to the point, right? Building an AI system security plan. I'd like to start with zero trust because I think as a foundation, every organization has to look at zero trust architecture and implementation as a foundation. Then on top of that, we build our AI security plan. And then we're going to talk about AI governance, risk management, compliance, and audit. And a key takeaway is the development of an action plan for building AI system security plan to protect those high-risk AI systems. So here's a diagram I use for all the class. I teach at UMass in their masters in cybersecurity. I teach two classes. I teach a class on building a security program. I teach a class on ransomware program. I teach this AI class. And all of them I use the same diagram because I like to show this as a model of threats, vulnerabilities, security controls, and assets. In this case, we're talking about assets. We're talking about high-risk AI systems and cloud infrastructure, which are the landing zones where those AI systems are deployed on. That's part one. Part two, we're going to talk about the threats, the vulnerabilities, and the controls. And then part three is the deliverable, a risk-based AI system security plan to manage those AI risks to high-risk systems. So let's start with how AI systems work. We are talking about traditional software development versus a machine learning or AI software development. Characteristics of traditional software: explicit rule definition, deterministic behavior, predictable system responses, a testing methodology to verify measured against the predefined specs, and performance optimization based on code optimization, algorithm selection. The code really runs the output. When we talk about AI software development, it follows a data-driven approach versus a specification-driven approach. The development characteristics: data-centric design, programs based on data. Non-deterministic behavior: the outcome is not predictable. The outcome is now probabilistic based on system responses. We have an evaluation methodology. We measure against these validation data sets. And performance optimization: we tune the parameters of the model as well as the architecture to get it to where we want it to deliver the model so it acts within the allowable safety factor of the outcome that we're looking for. And then we could go ahead and deploy it once we've reached that particular state. So traditional software programs are rules-based. They produce output or results when given input or data and a program or an algorithm, whereas AI software programs learn from training data instead of defined rules, are tuned to make decisions or predictions based on patterns. So these diagrams show the difference. Traditional modeling starts with data and a model to develop a computer program and the output as a result, Whereas machine learning is iterative. We go through training stages. So we start with sample data and an expected result. From there, we build a model. And then the model is then pushed back through with new data or training data to update that computer program until such time as we reach the result that we're looking for within that range of the probabilistic output that we're looking for. So it's an iterative process to arrive at the correct result. The big benefit, of course, is we can provide it with much more data and we can get much deeper results because we're not limited to a specification-driven approach. We're now using a data-driven approach. So we want to talk about how the systems work, looking at the architecture and the workflow, starting with the architecture. We start with data. We have structured and unstructured data. That data is stored in databases and on servers. It is then processed by the models, the AI models, those circles that you see, which include artificial intelligence, machine learning, deep learning, generative AI, which feed large language models, and generative AI, which also feed AI agents. We'll talk about both. And then ultimately, we have predicted signals are generated based on the data output. And again, we iterate that until we reach the desired model for the particular problem that we're trying to solve. As far as the system workflow, we start with data preparation. Data preparation includes cleansing, feature augmentation, standardization, deduplication. We then train the model. We train the selected model using the training data. It learns patterns, relationships within the labeled data sets. We fine-tune the model, enhance the model performance. We add hyperparameters, learning rates, batch sizes. And then finally, we test it with inference or deployment, which is actual real data. The trained model is deployed to perform its job in a process known as inference or predictions, and it generates output based on new unseen data to solve a domain-specific problem, like a healthcare problem, or a financial services problem, or a higher education, human capital management problem, as we discussed with the Oracle system. So generative AI versus agentic AI. So with generative AI, models that learn from data about existing artifacts use this to generate new artifacts, and they're based on foundation models, which are large-scale AI models that are trained on massive, diverse data sets that are adapted to many different downstream tasks. For example, Google Cloud, Google Model Garden has 200 foundation models. Amazon Bedrock Marketplace has 100 foundation models. Microsoft Foundry has 11,000 foundation models, which include Hugging Face and other repositories, GitHub, for example, where those models are stored. Once we have those foundation models, we select the foundation model. We can build on top of that a large language model, which is a type of AI designed to understand, generate, process human language, such as Google Gemini, Anthropic Claude, OpenAI, ChatGPT. And we have AI chatbots, which are conversational applications built on top of a large language model. So what is the workflow for generative AI? It's data collection, examples of the type of content to be generated, model training, learn from underlying patterns and data structures, generation, the model learns from training data, and then refinement, improve the quality to meet specific requirements. Next, we have agentic model. And these are more of the norm lately. There's been a lot more deployment of agentic AI in the last, I would say, 5 or 6 months. AI models that can reason, plan, execute multi-step tasks based on human intervention or without human intervention. We have perception, reasoning, action, and learning. Perception is collect and process data to understand the environment. Reasoning is to analyze data to determine the best course of action. Action, this is new, this is different than generative AI. Execute decisions to complete tasks or trigger response. So agentic AI actually takes action. And we also learn from past actions to improve future decisions. Key characteristics: autonomy, operate independently with minimal human supervision. Decision making, analyze situations, weigh options, and determine actions. Goal-oriented behavior, break down complex tasks to manageable steps. Adaptability, adjust behavior based on new information or circumstances. Natural language processing, complex instructions in human language. And workflow optimization, execute and manage multi-step process. So how is AI developed and how is AI deployed? So this diagram on the left shows the development and the deployment process. We start with the objectives. We select the models. Once again, foundation models are selected. We then prepare the data. We train and customize the model, and that is the development stage. Then we deploy the systems, we monitor and maintain those systems to make sure they meet our requirements. So the phases include defining objectives, ensures technical and business outcomes meet organizational goals. We select the models. We want to choose the models that best fit the use case. We want to prepare the data beyond cleaning and labeling. We have privacy concerns that we have to focus on in industries such as healthcare. We want to train, customize the model, includes training from scratch or fine tuning. And then we deploy. We deploy in a cloud platform like Azure AI Foundry, Google Vertex AI, Amazon Bedrock, which we mentioned before. They have the foundation models, provide scaling and optimization. And then we monitor and maintain, ensure the ongoing alignment with initial objectives, and helps prevent model degradation over time. So here are the different options for deployment. On the left, we build our own. On the right is the supply chain. We consume AI in apps. So that's like supply chain risk management or third-party apps. So when we build our own, we start with a foundation model, fine-tune it, retrieve the data, prompt engineering, and then ultimately the application is developed. That's build your own or infrastructure as a service. Next, we could have AI models that are extended via fine tuning, where we start with a foundation model from Google, Amazon, or Google, Amazon, or Microsoft, for example. We fine tune those models. Then we do the data retrieval, our particular data that we want to incorporate, and the prompt engineering based on our design, ultimately build the application. We could then bring a model, platform as a service, where the foundation model exists and the fine tuning exists, and then we build our model. We build on top of the foundation model that was provided by one of the cloud providers, the data retrieval, prompt engineering functions we would do, and then build the application on top of that. Or we could, customize an application where the foundation model, the fine tuning, the data retrieval is done by the provider, and we just customize that application. Or we could go software as a service. We could buy a model. We could consume an AI embedded in application. So we have those different options for AI deployment. So let's talk about some use cases. We'll start with Google Vertex AI, which is a foundation model that supports Google Gemini, is one of the applications or one of the foundations that you can build. The Vertex AI is the foundation model. They have over 200 of those, but you can build Gemini on top of the Vertex AI foundation model. So the architecture is shown on the left. Has Vertex AI Studio. We have a filter responsible in AI and safety. We have the actual foundation models, and then we have the customization where we actually build our own model in the customization. We have grounding and RAG function calling, as well as citation checks. So it starts with a prompt, request consisting of text, images, video, audio, documents, etc., sent to a generative AI model to elicit a response. We have the foundation models, which prompt sent to a generative AI model for response generation. Vertex AI models include Gemini API. Customize the model, customize the default behavior of the model via model tuning. We want to ground the model. It connects the model's response as a source of truth, which really looks at the data that's being processed in the model. RAG stands for retrieval augmented generation. We want to make sure that that data is trustworthy to reduce hallucinations. We also do a citation check. Vertex AI checks citations, responsible safety layer, and then the response. The prompt and response pass the filter checks. The response is then returned to the requester. Next, we have the Open Evidence Medical Information Platform. And here we also have the two processes. We have the build process and we have the use process. So again, Open Evidence was one my son uses. It aggregates, synthesizes, and visualizes clinically relevant peer-reviewed medical literature in understandable, accessible formats healthcare professionals use to make more evidence-based decisions. My son uses this. He's a surgeon, so he uses to make sure he has the latest information on a particular surgery that he does before he goes into the operating room. He wants to make sure he's got up-to-date information, so he uses Open Evidence Medical Information Platform to make sure that he is up-to-date with surgical techniques. So the process we see on the left is a file upload build. This is how we get the data into Open Evidence. In the next slide, I'll show you how my son, for example, a user, we get the information out of Open Evidence. Step one, we upload project files to a scalable, secure, durable data storage. Step two, we transfer it to deployment by executing a builder. That build container ultimately feeds the application. Then we ping an API endpoint, tracks deployment status. Step four, the build container provisions resources. And then step five, once resources are provisioned, a deployment database document is created and the metadata is uploaded to static storage. And that's the next point, is we start now with static storage where the data is, and then a user request and response process. Step one, the user performs a DNS lookup, connects to the nearest edge location of Open Evidence Medical Information Platform. Step two, the request is routed to reverse proxy for rewriting and proxying requests. Step three, the AI gateway determines which deployment version should be served to a user based on the host name of the incoming request. In other words, the AI gateway determines frequent requests or responses from a particular user and determines which version should be served back to that user. The AI gateway downloads the resources from the static storage. You can see the static storage on the left with serverless functions, image optimization, edge functions. All those capabilities are fed to the gateway. And the responses get cached to speed up future lookups. So those are examples of large language models. Next, we want to talk about agentic AI systems. So agentic AI systems have multiple agents. Like in this case, I show agent 1, agent 2, agent 3, agent 4, and they report back to a coordinating agent which interfaces with the application. So in the next two slides, we're going to talk about two different use cases: a medical appointment booking, where the coordinating agent is a supervisor agent, and the agent 1, 2, 3 are doctor availability, doctor booking, doctor frequently asked questions. These are agents that have specific tasks to go out and determine the availability, the booking of the appointment, and frequently asked questions about the particular medical doctor, in this case, that provides the services. And it's all done through the coordinating agent. So here's the example. It's a multi-agent booking system where an AI system is composed of multiple independent interactive agents capable of perceiving the environment and taking actions. The system can work towards a common goal. And we have three steps. It begins with a user prompt. It could be a request from a human user, software process, etc. Step two, communicating with the user through these agents. A supervisor agent coordinates the workflow. And then step three, the sub-agents, if there's availability, a booking, and a frequently asked question agent, return their output to the supervisor agent that finishes the booking for the particular doctor. Another example, again, is the Oracle Fusion Cloud Human Capital Management Benefits Advisor. And in this case, we have agents that look at medical benefits for a particular user for an organization that has deployed Oracle Human Capital Management as their benefits, or as their HR system. So it's a comprehensive cloud-based software suite designed to manage an employee's entire life cycle from the moment they're hired to the day they retire. And we're specifically focusing on the benefits advisor portion from the United Healthcare Preferred Provider Organization, or PPO, which is one of the benefits capabilities that's provided by Oracle's Human Capital Management. So it's a five-step process in this case. An employee initiates an interaction by submitting a request to Oracle HCM. Oracle HCM agent intercepts that request and decomposes it into subtasks executed sequentially. So that's like the supervisor, and here we call it the agent orchestrator. They identify the function to achieve relevant details. In this case, we're looking at how much we paid towards an annual deductible. So it receives information from the application that we've already paid $760 towards the deductible. Now we have to go out and look at the policy to see what is the annual deductible. So step four goes to an agent that retrieves the benefit plan details from the knowledge base, which is part of the Oracle application. And it states that the annual deductible is $2,000. And there's a calculator tool that computes the result, basically subtracting the amount that's already been paid, $760, towards the deductible from the annual deductible of $2,000, and it provides the response back to the end user. The remaining deductible is $1,240. So that's an example of how an AI agent is worked in an application. I've used Oracle as the example. In the class I teach, I go through ServiceNow, I go through Salesforce, I go through Workday. They all use agents in their applications. So that's a little bit about AI, how it works, and how it's deployed. Now let's talk about the threats, the vulnerabilities, and the security controls, all shown by those yellow boxes. We have a threat zone, a vulnerability and security control zone. So we'll now take a look at that. So we start with adversarial AI attacks. They manipulate AI models by feeding them deceptive data, cause incorrect or unintended behavior. Same as attacks against systems today. They exploit vulnerabilities in the logic of the model through subtle, imperceptible changes to the input data. So here's the steps for an adversarial AI attack. Step one, understand the target system by studying the algorithms, data processing, decision making. Number two, create an adversarial input that exploits the weakness. Step three, exploit the system, make the system behave unpredictably or incorrectly. And step four, post-attack actions can range from misclassification of images or text to potentially life-threatening situation in critical applications. Think of an autonomous vehicle. If they modify a stop sign to actually be a speed limit sign, then the vehicle could read that as speed limit and continue right through a stop sign, for example. So that'd be an example of a post-action or a post-attack action in an autonomous vehicle. So what are the top 7 adversarial AI attacks? It starts with data poisoning, where the attackers modify a data set, inject the data set with a new specifically doctored portion of data. It could be a model evasion attack. Adversaries manipulate the model input to make an incorrect prediction. A backdoor attack, where they control shadow logic and override the model's instructions, compromising the model reliability. These last two are about attacks against models. We could have model theft, model extraction, where they reverse engineer a model's functionality, steal proprietary knowledge and sensitive training data. We could also attack the prompt injection attack, embed additional instructions in an LLM query to manipulate a model's output. Or a supply chain attack. We target trusted third-party vendors who offer services or software. Or a shadow AI attack, unsanctioned use of AI by employees without the formal approval or oversight of the IT department. And the risk there is to expose sensitive data from the organization. So now let's talk about the vulnerabilities. It starts with prompt injection. It manipulates a large language model through crafty inputs, causing unintended actions by the LLM. We have sensitive data disclosure, which is including PII, financial health, business data that is disclosed. We have supply chain. We still have supply chain risks, third-party risks in LLMs, the same way we do in traditional software programs, where the supply chains face risks in training data, models, platforms, causing bias, breaches, or failures. We have to make sure that our supply chains are secure. It's not just the models that we develop and deploy ourselves, it's also our supply chain. We have data and model poisoning, which manipulates pre-training, fine-tuning embedded data, causing vulnerabilities, biases, or backdoors. We have improper output handling, which involves inadequate validation of LLM outputs before the downstream use. We have excessive agency, which they gain agency via extensions, tools, or plugins, act on prompt. It basically gives you too many permissions within the model. We have system prompt leakage, when sensitive information in the prompts is intentionally exposed. We have vector and embedded weaknesses, which involve RAG with LLMs, which is RAG is when you connect to outside data sources. So we could have weak vectors and embeddings within the RAG, regenerative adversarial networks. We could have misinformation. It occurs when false but credible outputs mislead users, risking security breaches, misinformation, or unbounded consumption when LLMs generate outputs from inputs, relying on inference to apply learned patterns. Here's a diagram that shows where each of these OWASP top vulnerabilities occur within an application, within a model, or an external data source, or an application which is shown on that server-side function trust boundary 2. So trust boundary 1 actually shows the AI model. Trust boundary 2 shows the application that the model connects to, and trust boundary 3 is actually the augmented data or the private data stores that are fed back to the model to give the model additional data. We also have vulnerabilities within the fine-tuning of the data, the training of the data, but this diagram shows where those different vulnerabilities would occur within AI deployment. So next, let's talk about security controls. And we're going to start with the NIST 800-218A, Secure Software Development Framework for Generative AI. Is comprised of 4 practices and 20 tasks. The practices are prepare the organization, produce well-structured software, protect the software, and respond to vulnerabilities. And we'll walk through what those different tasks are as well. So the Secure Software Development Framework provides a common language describing secure software development practices through the software development lifecycle. Again, this is looking at an AI model under development. It's intended to be used in conjunction with NIST 800-218, which is the Secure Software Development Framework version 1.1 for traditional software programs. The scope is, this case is the AI model development. It includes data sourcing for designing, training, fine-tuning, and evaluating AI models, incorporating, integrating AI models into other software. It helps AI model producers reduce the vulnerabilities in the AI models, reduce potential impacts of the exploitation of undetected or unaddressed vulnerabilities, and address the root cause of vulnerabilities to prevent recurrences. So here are the different practices and the tasks. Under prepare the organization, we have a total of 5 different tasks: define security requirements, implement roles, responsibilities, implement supporting tool chains, define and use criteria for security checks, implement, maintain secure environments for software development. Under the protecting the software, we have protect all forms of code and data from unauthorized access, provide a mechanism for verifying software release integrity, archive and protect each software release. For producing well-structured software, we have design software to meet security requirements, review the software design to verify compliance with security requirements, confirm the integrity of training, testing, fine-tuning, protect software for, reuse existing well-secured software when feasible. 5 is create source code by adhering to secure coding practices. 6, configure the compilation, interpreter, and build process to improve security. 7, review and analyze human readable code to identify vulnerabilities, verify compliance with security requirements. 8 is to test the code to identify vulnerabilities and verify compliance. And 9 is to configure the software to have security settings by default. And then finally, we have respond to vulnerabilities, where we want to identify and confirm vulnerabilities on an ongoing basis, assess, prioritize, remediate vulnerabilities, analyze vulnerabilities to identify their root causes.
Larry, I'm going to give you a chance to catch your breath here. I
Oh,
have 2
thank you.
questions. Yeah, of course. First one, I know a few folks asked about the slides. I had posted the file directly in the Zoom chat, but it seems that it was kind of viewable but not downloadable. So I just posted another link in the Zoom chat. That's a direct download. So the second you click that link, it'll start a download in your browser. And that's the PowerPoint file that Larry is working off of right now. The second question is for you, Larry. Are there
Yes.
any pre-release or released versions of existing cyber/info security frameworks that are updated for AI?
Yes. The NIST cybersecurity framework, right, is now updated for AI, was just done last December. The Cloud Security Alliance AI Controls Matrix was updated for AI as well. And the third one is this one we just talked about, right? The Secure Software Development Framework for AI, which is the NIST. So NIST has the Secure Software Development Framework, is looking at software under development, either AI or traditional software. So they have both, right? They have the traditional software development framework, and now they have the AI software development framework. NIST has the NIST cybersecurity framework for traditional software, and now they've updated it for AI as well. So the NIST cybersecurity framework. And then one that I didn't include, I included in my full day class, is the Cloud Security Alliance has the AI controls matrix. Of course, the Cloud Security Alliance had the controls matrix prior to AI, and now they have an updated version that includes AI. So yes, that's a great question, and there are, updates on traditional frameworks.
Perfect. Thank you, Larry. I was going to follow up and ask you if there are any frameworks you know of that are not updated yet, but are currently in the works to be updated. But I'm going to guess the answer is probably all of them. They're
I'm
probably all.
assuming, yeah. One of the things, and this is one of the things I meant to mention, is there's not going to be a shortage of frameworks around AI, right? It's just, phew. And for me, when I was practicing as a CISO, I would always look at two or three frameworks when I built a security program because they first of all because they're all out there, right? And I wanted to make sure that I didn't miss something, right? I didn't overlook something. So I think it's good practice to look at two or three. Once you really understand your assets and you really understand your technology that you're using to implement security, it's not a huge heavy lift to map them back to the security controls. So that's a great question. If I'm responsible for securing a particular AI application, I'm going to look at multiple frameworks because I want to be sure, right? Because I don't want to get that call in the middle of the night where we have a security incident, right? And it was something that I may have overlooked and didn't have the right controls. I feel much better if I've done everything I can in advance and then there happens to be an incident versus if I took a shortcut and really didn't look at all the different possibilities. So that's how I always did this. In my 15 years as a CISO, that's how I always did that. So
Thank
great
you so
question.
thank you so much, Larry.
Oh, you're welcome.
I have another question actually.
Yeah.
Question coming all the way from Costa Rica.
Oh boy.
Is MITRE Atlas the correct framework for vulnerability analysis of AI security implementation?
Well, I may have to go to Costa Rica to answer that question, but no. MITRE Atlas is the AI threat framework. It's MITRE's version of threats, right? So it's great point. MITRE has the Atlas framework. I didn't have a chance to include it here, but I have it in my class. The MITRE Atlas framework looks at threats. It looks at, the tactics, techniques, and procedures for attackers. So it's based on the MITRE ATT&CK framework. Okay, so it's a good question. So it's not really looking at vulnerabilities like OWASP is. OWASP is looking for vulnerabilities, whereas MITRE is looking for attacks.
Perfect. Thank you
Yeah.
so much, Larry. That is one piece I did forget to mention as I was kind of introducing Larry is that what you guys are getting today is a highly condensed version of a full day
Yeah.
course that Larry delivers that's over 300 slides. He does it often at the Secure Worlds, and many folks have probably seen him there. He's going to be doing it at the Secure World Boston coming up in April. But you guys are getting a very condensed version of a full day session that Larry does all over the place. If you guys want to ask any other questions, feel free to post them in the chat. I'll pause Larry as they come in. Thank you so much, Larry.
Oh, thank you. Thank you, Nick. And thank you for your questions. So that was the Secure Software Development Framework for AI. That's NIST framework. Now this is a new one, right? Google AI framework, Secure AI framework from Google, which I think is excellent. I found it not only does it do a good job of describing the security controls, it does a better job of looking at the threats, which you can see they call them risks, the 15 threats that you see there on the right-hand side, and it maps them against an AI architecture. And they have four components of their AI architecture, pretty much what we talked about before. We have the data, the model, the application, and the infrastructure. And this is why I'm really highlighting the need when we get into the actual building of the security program to look at zero trust as well, because we want to make sure the infrastructure is also secure, because we can secure the model, we can secure the application, but if our infrastructure is not secure, then no matter what we put into that infrastructure, what we deploy within that infrastructure, it's going to have risk. So this is the Google Secure AI framework, and it's used for building and deploying AI responsibly. Here we have 15 different risks that Google maps, and they include data poisoning, unauthorized training data, model source tampering, excessive data handling, model exfiltration, model deployment tampering, denial of ML service, model reverse engineering, insecure integrated components, prompt engineering, model evasion, sensitive data disclosure, inferred sensitive data, insecure model output, and rogue actions, which are similar to the ones we talked about earlier, but they go a little bit deeper on some of these. So let's take a look at the data controls. And basically what Google does is it breaks it into components. It talks about the data controls, the infrastructure controls, it talks about the model controls, it talks about the application controls, it talks about the governance controls and the risk controls. So those are the 6 areas that we're going to focus on. And it maps it to these particular risks. So the control for privacy enhancing technology, which says use technologies that minimize, de-identify, or restrict the use of PII data in training or in evaluation. The mapping is to what we just talked about, sensitive data disclosure, and who can implement. This is also a good thing for Google. They say in this case, the model creator or the developer can implement. We have training data management, ensure that all data used to train, evaluate the models is authorized for the intended purpose. Maps to those risks, which we just discussed, inferred sensitive data, unauthorized training data, and who can implement model creators again, or the developers. Training data sanitization, detect and remove or remediate poison sensitive data in training and evaluation. The risk is data poisoning, unauthorized training data. Who can implement model creators? And I'm just doing a high level on this. It's a very detailed document that Google has, and it's up on their website. And I've given you the link here. I have to go through this quickly because we don't have that much time. We have user data management, store, process, use all user data, prompts, logs from AI applications, mapping to sensitive data disclosure, excessive data handling. In this case, we have both the model creator and the model consumers that implement these controls, the user data management controls, because you can implement those controls both under development and implement those controls as a consumer in deployment. Next, we have infrastructure controls, model and data inventory management. The risk mapping is data poisoning, model source tampering, model exfiltration. The implementers are the creators and the consumers, if the consumers are storing the models, right? If it's not software as a service or a third party. Model and data access, minimize the internal access to models, weights, data sets in storage and in production. Who's risk? Data poison, or what are the risks? Data poisoning, model source tampering, model exfiltration, creators and consumers if storing the models. And I guess I probably spoke a little bit. We're talking about infrastructure controls. So we're talking about public cloud versus private cloud, for example. And in public cloud, you're going to want to make sure that the cloud provider has the capabilities for securing by building these. And it depends on if you have platform as a service or infrastructure as a service. So you get the idea. These all relate back to those implementation models. We have model and data integrity, ensure the data, the models, and the code produce models that are integrity protected. The risks are data poisoning, model source tampering, model exfiltration. Creators and consumers can both be responsible for implementing. And then finally, secure by default ML tooling, frameworks, libraries, software systems. And here we have 4 different risks: data poisoning, model source tampering, model exfiltration, model deployment tampering. Both the creators and the consumers would be responsible. Next, we have the model controls. We have input validation and sanitization, where we want to block or restrict adversarial queries. Prompt injection is the risk, and creators and consumers are responsible. Output validation, block, nullify, sanitize, secure output. Prompt injection, rogue action, sensitive disclosure, inferred, sensitive data, creators and consumers can implement. Adversarial training and testing. This is a big one. We definitely want to do a lot of red teaming. We want to do a lot of threat modeling. We want to do a pen testing, use techniques to make AI models robust to adversarial inputs in the context of their use. The risks are model invasion, prompt injection, sensitive data disclosure, inferred sensitive data, insecure model output. Creators and consumers should be doing that testing. We should be doing the testing, static dynamic testing during development, and we want to be doing, again, the red teaming, the threat modeling, and the pen testing during deployment. Next, we have, and I'm focusing here on the high-risk AI systems. We'll talk about what those are towards the end. When we get into governance, risk, and compliance, we'll talk about what high-risk applications are, those that are under compliance regulations, such as the European AI Act, the EU AI Act, as well as the Colorado AI Act. So now we have application controls, looking at the application itself. Ensure only authorized users and endpoints can access the resources. We have risks of denial of ML service, model reverse engineering. Consumers, now when you think it's in deployment, the consumers are mostly focused on these controls once the application has been deployed. We've got user transparency, minimize internal access. Anytime about access is going to be given off to the consumers, right? Access to models, weights, etc. Sensitive data disclosure, excessive data handling, the model consumer. Agent plugin user control, ensure the approval for any actions performed by agents or plugins that alter user data. Sensitive data disclosure, rogue actions, model consumers. Agent plugin permissions, least privileges to minimize the number of tools. Insecure integrated systems, sensitive data disclosure, rogue actions, model consumers, implement those controls. And then next we have the assurance controls, red teaming, which we talked about earlier, which is identify security and privacy improvements through self-driven adversarial attacks. Creators and consumers both should be doing red teaming. We have vulnerability management, proactively and continually test or monitor production environment. Risk mapping, all the risks. Just like red teaming is all the risks, vulnerability management, all the risk, creators, consumers, threat detection, all the risk, creators, consumers. We want to look at vulnerabilities, threats, both in development and in deployment. Same with incident response, managed response to AI security and privacy, all the risks. So this kind of gives you an idea that, okay, we're going to be doing an awful lot to make sure that these models are secure if we're going to be following the Google Secure AI framework. And then finally, we have governance controls, policies, education, model consumers, because they're deploying the model, internal policies and education, AI security and privacy policies. Everybody, the creators as well as the consumers need to have internal policies and education versus the user policies and education would be more on the consumers. Product governance, validate that all models and products meet the established security and privacy. This is kind of the catch-all term saying go back and make sure you have an assessment done to make sure that that product is in fact secure against all risks. And then finally, risk governance, inventory, measure, monitor residual risks, all controls and model creators and model consumers. So I think this is obviously a new framework from Google looking at AI. And the last one I'm going to cover is the OWASP, AI threat model with controls. So everything in blue is the AI model. Just like the Google AI model, this is the AI model from OWASP. And they break it into two pieces. The top piece is during development. The second piece, the lower piece, is during runtime. And they talk about the different threats, evasion, model theft, model inversion, data disclosure, membership inference, denial of service, prompt injection is during deployment, and some of the threats during development, training data leak, training data poisoning, model theft, model poisoning, for example. But what we really want to focus on are the security controls, and there are five different categories of controls. We have the AI governance controls, the technical IT security controls, the data science, data focus controls, the data protection controls, and the model controls. And here's a description of what those all are. And I haven't gone into detail, but if you go into the OWASP documentation, you'll get a detailed description of each one of these controls. Like, for example, governance controls is AI program, security program, development program, secure development program. Just like what we're doing when we walk through this slide deck is to get to an AI program or an AI security program. We have technical controls in development security, segregate the data, supply chain manage, and discrete. Runtime controls that are technical, runtime model integrity, runtime model input-output integrity, runtime model confidentiality, runtime input-output confidentiality, encode model output, limit resources. I know these because I've talked this many times. But anyway, you can look these up and you get a detailed description of what these are. And again, there's five different areas of focus: governance, technical security controls, risk-based data science controls focused on the data. And then number four is limit the data at rest and in transit. And finally, control the model behavior for oversight, least privileges, anti-transparency, et cetera. So I know that was very quick, but that's a summary of what the security controls. Now, to build a security program, we're going to have to take those controls, apply those to the assets, and then we come out with a system security plan. So I like to start with zero trust because I don't want people to forget about this. Zero trust is a paradigm focused on resource protection, the premise that trust is never granted implicitly, it must be continually evaluated. Architecture encompasses identity, the person and the non-person identity, the credentials, access management, operation, endpoint, hosting environment, and interconnecting infrastructure. The focus is on restricting resources that those that have a need to access and grant the minimum privileges, read, write, delete to perform the mission. The tenets of zero trust are all data sources, computing services are resources, all communications is secured regardless of network location. Access to enterprise resources granted on a per session basis. So every single session needs to be authenticated. Access to resources is determined by a dynamic policy, includes the state of client identity, application service, requesting assets. The enterprise monitors and measures the integrity and security posture. All resource authentication authorization are dynamic and strictly enforced, and the enterprise collects as much information as possible about the current state of the assets, network, communications, use it to improve the security posture. This diagram on the left shows the zero trust architecture according to NIST. Here we have a logical components as well as data sources. The logical components are shown in red. The data sources are shown on the perimeter. So the three logical components are the policy engine, the policy administrator, and the policy enforcement point. The policy engine is responsible for decision to grant access to a resource for a subject. So you see at the bottom under the data plane, the subject who connects to a system is requesting access to an enterprise resource. The policy engine up top makes that decision. The policy administrator is responsible for taking that decision and establishing or shutting down the communication path between a subject and a resource. And they do that by sending commands to the policy enforcement point, which actually enables, monitors, and eventually terminates connections. So the idea here is the control plane, which includes the policy engine and the policy administrator, they make the decision, whereas the data plane, which is the policy enforcement point, actually takes action. And in this case, they decided to enable, to monitor, or to block the connection from the subject to a resource. And those connections and policies are based on data sources, such as continuous diagnostics and mitigation, information about the assets, patched operating system, approved software, known vulnerabilities, industry compliance, which are policy rules that ensure regulatory compliance, threat intelligence, information from internal, external sources, including attacks, malware, vulnerabilities. We just talked about that. Network and system activity aggregates asset logs, network traffic, access actions for real-time security posture of information systems. Data access policies are attributes, rules, policies for access to resources, basic access privileges. Enterprise PKI, which are the certificates for access issued by the enterprise. We have identity management, responsible for creating, storing, and managing enterprise accounts. And we have the SIM or system, which is a security centric information for subsequent analysis. They collect the logs for subsequent analysis. So those are all the data sources. So the idea here is if you're building a zero trust implementation in a zero trust architecture, then you have to make sure that you have something in place, technology or capability to perform all of these 8 data functions as well as those logical components, policy engine, policy administrator, policy enforcement point. And I really would encourage everybody to go back and say, okay, where are we on zero trust? At the same time, we're looking to implement AI. We want to make sure that we have implemented zero trust within our organization. These are the 3 models that have been developed by NIST. We have zero trust, including enhanced identity governance, where the policy engine, the policy administrator just looks like the previous diagram. Resource access is based on access privileges granted to the given subject. We have the zero trust using device agents and gateways. So we have an agent in the enterprise system that the subject accesses and a gateway in the data resource, which is the recipient of the connection. So the policy enforcement points has 2 components. One is an agent and one is a gateway. And the agent coordinates the connection and the gateway serves as a proxy, front ends the actual resource. And then now what we've done is we take that gateway and resource and put it in a resource enclave or a cloud, and the cloud now performs that gateway function. Same idea as the middle one, except for now we have still the agent on the system, but the gateway is separated from the resource. We have multiple resources in the cloud, but a front-end gateway that determines whether or not a connection is allowed or denied from a particular subject trying to get access to a particular resource. So those are the 3 different deployment models that have been defined by NIST. Now, what's interesting is the deployment cycle is what we're going to also talk about for building an AI security program. We follow the NIST risk management framework, and I've been doing this since it was first published. I think the version 2 was first published in 2012. So there is a 7-step process. Prepare the organization, categorize the system, meaning what systems are we trying to actually protect. Select the security controls. We talked about that earlier. We have many different security controls. I like to do 2 or 3 different security control standards and walk through this process. implement the security controls, assess the security controls, authorize the system by some other individual checking your work, making sure that you haven't missed anything, and then monitor, continuous monitoring, and then it loops back to repeat that process. I like to do it every 6 months. I think what you're going to probably be required to do is every 12 months, but you want to repeat that process to make sure that nothing has changed over that time interval. And zero trust, according to this slide, is a journey. Most enterprises operate in a hybrid, perimeter-based mode, but the idea is you should have a strategy and a plan that's going to get you there. That's kind of my prerequisite for AI, or doing it at the same time when you implement AI. Too many people have legacy systems. Too many people have technical debt. You really need to focus on bringing your infrastructure, bringing your assets up to date, implement a zero trust application or architecture, a zero trust implementation, so that now you're prepared for the future. So now let's talk about developing a security, privacy, supply chain risk management plan. This is a document that was published last June of 2025, NIST 800-18 Rev 2, which really has a good detailed description of how to develop a security, privacy, supply chain risk management plan, because we want to look at all three. And we want one document that really tells us how to do all three. So the system security plan describes the security requirements involving the systems outside the authorization boundary, including the controls that protect the system and information. We want the system privacy plan describes the privacy requirements, controls that address predictability, manageability, dissociability. And then the supply chain risk management plan, which is third-party risk, describes the requirements, including controls to manage, implement, and monitor the supply chain. On the right, we have mapping to 837R2, which is, again, the risk management framework we just talked about when we talked about zero trust. So we're going to use the same framework, the same 7 steps when we implement a AI security program as we did for a zero trust program. The outputs include the system's purpose, the environment of operation, the information stored, processed, and transmitted, the data flows, the architectures, the control implementation details, the roles and responsibilities. So here's the details of the system plan. We have the authorization boundary, individuals responsible, organization security, privacy, supply chain risk management controls, the capabilities to defend against threats. Again, 3 different: the system security plan, the privacy plan, the supply chain risk management plan. We're going to focus again on the system security plan because that's kind of what we're looking at for AI security. On the right, we have section 3, system name and identifier, plan reviewers, responsible personnel, operational status, description, information types, authorization boundaries. We have to have architecture diagrams. We have to have data flow diagrams. We have to understand what we're actually trying to protect. We have to have the control details. Which controls are we going to implement? Information exchanges, which systems participate inside the scope of the assessment, the laws, the regulations, the policies, the digital identity acceptance, reference to art attacks and acronyms. So again, we're going to follow the risk management framework, which is a 7-step process for building a security program. And it's been updated last summer. They've added an 8th step, which I'll briefly mention when I go through this. Step 1 of the risk management framework: prepare the organization, define the authorization boundary. What's the scope of what we're doing for an assessment? Who are the stakeholders? What is the business focus? In other words, why do we care? Is this a high-risk AI system? That's why we care, right? The information types it handles, the data flows, the third-party services. Then we want to categorize the impact of the loss, which is basically saying why it is a high-risk system. We then select the security controls, step 3, which we talked about. We have several options. We have the secure software development framework for AI if we're looking at securing and building a security plan for development, Google AI framework, or the OWASP, or the NIST cybersecurity framework for AI, or the cloud security framework for AI if it's in deployment. So we want to look at both. If we're developing, we have to have a security program around development. If we're deploying, we need a security program around deployment. We want to then implement the security controls. Then we want to assess the controls. Where are we currently with our security? How do we compare to where we want to be? And then we want to authorize the system. Control provider assembles a authorization package. Once we sign off, yeah, we're good where we are. We want to do continuous security monitoring. where we revise the control catalog, update the laws, update the system assessment, the weaknesses, changes that alter the system posture, changes to key personnel. And then we want to automate this system plan. This is the new step that was added this past summer with NIST 800-18 Rev 2. It's automate the system plan through the system lifecycle for the entire system lifecycle. So basically, it's an assessment of the information collected from systems inventory, personnel contacts, etc., changes, plan of action, and milestones, the protection levels, the access controls, the review and update the system information to support continuous monitoring, track changes, alter management of changes, etc. So that's the output. That's the deliverable, a system security plan. But we want to also make sure that we have in place a governance framework. And this governance framework, I like the Deloitte AI governance framework. It has these components: strategy, evaluate the integration of the company's AI approach to broader corporate strategy. How does AI fit in the corporate strategy? That's our strategy. The risk, understand, oversee the risk AI poses to the company's overall strategy. Is this a high risk AI system, or do we care? Governance, understand the significance of the board's governance of AI, includes the governance structure, board composition, etc. Performance, monitor the company's progress against AI specific financial, operational, and strategic goals. At some point, we need to update our governance function, our AI governance function, or our AI council, whatever you want to call that, with the current state of security. That's what performance is. We tell them the current state of security. We want to measure talent. Do we have the skills to execute the AI strategy? And then culture and integrity. Here we helped cultivate a culture of trustworthy AI. One of the different threats was shadow AI. We want to make sure that we let our employees know that that's not acceptable, because that's one way to disclose sensitive information through shadow AI. You have to be responsible to this board or this governance framework and make sure that you're only accessing AI systems at work based on what's allowed by this governance team. So that's governance. Next, we have risk management, and NIST also has an AI risk management framework, NIST AI 100-1. It has a total of four core functions, 19 categories and 72 subcategories. So it very much looks like the NIST cybersecurity framework in functions, categories, and subcategories. So the four functions are govern, a culture of risk management is cultivated and present. Map, context is recognized and risk related to context are identified. Measured, we have to measure. Identified risks are assessed and analyzed. And managed, risks are prioritized and acted upon. So the core functions include govern, map, measure, and manage. The categories are represented the actions that can achieve the particular core function's goal, and the subcategories are the desired outcomes relative to a specific category. So we have the categories, the actions, and the desired outcomes. So here are the categories and the actions for each of the four different core functions. The govern implements a culture of risk management. Here we have govern 1, policies and procedures. Govern 2, accountability for mapping, measuring, and managing. Govern 3, workforce diversity for mapping, measuring, managing. Govern 4, organizational culture, considers and communicates risk. And govern 5, processes in place for engagement with actors. Govern 6, policies and procedures, address AI risk from third-party software. And there are 20 subcategories under the govern function. Under the map function, establish the context to frame risk. This is where all kind of the details are. After completing the map function, the organization should have sufficient information for a go, no-go decision, whether to design, develop, or deploy the system. Here we have 5 different categories. Map 1, establish, understand the context, the AI system purpose, what its uses, and what are the risks to that AI system. Map 2, perform the AI system categorization, meaning where the technology is involved, where the components involved, development, deployment. Map 3, document AI capabilities, usage goals, expected benefits, and costs. Map 4, understand the system benefits and the risks, the third-party risks, and then characterize the impacts individuals, groups, communities, and organizations. Next, we have the measure function, which includes 4 categories, 22 subcategories. It employs tools and methodologies to analyze, assess, benchmark, and monitor risk. Measure 1, methods and metrics are identified. How are we going to measure? Measure two, systems are evaluated for trustworthy characteristics. This is where we do our assessment. Measure two. We're actually measuring risk at this point. Measure three, mechanisms in place for tracking those risks. And measure four, assess feedback about efficacy of the measurements. We want to make sure we agree with the output from the measure function. And then finally, 5.4 is the core function of managing. Manage allocates risk resources. So we actually allocate resources to the mapped and measured risks. We want to manage one is prioritize AI risks based on the assessment. Manage two, prepare and implement strategies to minimize risks. Manage three, risks and benefits from third parties are managed. And manage four, document monitor risk treatments, including third party. So that's a risk framework that supports our system security plan. So this is how we go back and we evaluate the risk with our current deployment versus where we want to be and prioritize those high risk items so that we can effectively mitigate those before deployment. Now I'm going to talk about a couple of governance frameworks, the European AI Act, and then I'll talk about the Colorado AI Act. So the key focus of the European AI Act is on category two, high risk systems. Category one, they call unacceptable risk systems. You cannot put those into play in the EU market. We're focused here, this whole talk is focused on high risk AI systems. AI systems that negatively affect safety or fundamental rights are considered high risks. Examples, biometrics, critical infrastructure, which we all do a lot of work with critical infrastructure, law enforcement, judicial democratic process. High-risk AI system can be deployed after risk mitigation. These are where we have to have a security plan. These are where we're going to have to make sure we do risk assessments, right? If we have limited risk systems, AI systems that interact with natural persons or generate content that would not qualify as high risk, chatbots, deepfakes. A lot of people are deploying those now without sensitive data. If it's sensitive data, it becomes a high risk. Can be deployed with minimal oversight and monitoring. You don't have to do such a thorough risk assessment for a limited risk. And the minimal risks deployed in the EU market, don't worry about it, right? So, what are the milestones for complying with the European AI Act? It started a year ago. Prohibited AI practices, banned certain AI systems. Employees involved with AI decision making have training on AI risk management. So by now, anybody who's involved in implementing, developing an AI system should have had some training in AI risk management and AI governance. Last August, 6 months ago, we had transparency disclosures. All providers must publicly disclose details, how you train your models, how you train your data, and what the inherent risks are. One of the things that's new about AI is a thing called a model card. And you'll see in a minute when we talk about audit, a model card describes how your model works and what the data sets are, how the model works, how it was trained, how it was tested, and how it was secured. So that was required as a transparency for high-risk systems last August, so you could explain and account for AI outputs to make sure they're understandable, predictable, and governed by clearly defined policies. That was 6 months ago. Now, 6 months in the future, they're going to really zero in on high-risk AI systems, healthcare, critical infrastructure, law enforcement. You must ensure AI high-risk systems of a rigorous risk management practice, bias detection, mitigation, and you have to maintain those security safeguards. So you almost have like this year coming up, as we're halfway through, to make sure that you have very good documentation around your high-risk AI systems. That's what this class is really all about. And then August of 2027, EU regulated industries such as medical devices, finance, automotive be subject to an extended compliance timeline, and all systems or AI systems requiring pre-market conformity assessments under sector-specific EU laws must meet full AI Act compliance by August of 2027. Okay, so let's compare that to the Colorado AI Act. This is the first state to enact a comprehensive law relating to the deployment and the development of AI systems. It was enacted of May of 2024, and that's really when I started teaching this class around that time. Actually, I started teaching this class, about May of 2024. It will go in effect June of 2026, so this coming summer, it will go in effect. Focus on development, deploying high-risk systems, adopts a risk-rates approach, and it really looks like the EU AI Act. Key points, they actually try to define a high-risk AI system. It is a system that makes a consequential decision. They relate to education, employment, financial services, housing, healthcare, legal services. It's designed to protect algorithmic discrimination, unlawful differential treatment, imposes obligations related to documentation, disclosures, risk analysis, governance, impact assessments for developers and deployers that are building or developing high-risk AI systems. Steps that companies should consider. Develop a statement of purpose, the intended use case. Why are you building this high-risk AI system? Adhere to the NIST risk management framework, which we just covered, or another comparable nationally, internationally recognized framework. ISO has one as well. 42,000 is the ISO risk management framework. Just like multiple security frameworks, there are multiple risk frameworks as well. Begin developing documentation that will be required for developers and deployers for both. Start creating the necessary infrastructure, principles, processes, and to perform impact assessments, conduct annual system reviews, and if planning to claim an exemption, consider the documentation that's required. And then finally, we're talking about how do we audit these things. So the European Data Protection Board is responsible for auditing GDPR and other AI, and in this case, an AI. They develop an AI audit checklist that focuses on the EU AI Act. So in their audit checklist, it's called the End-to-End Socio-Technical Algorithmic Audit, or E2EST/AA. It provides a template, and you can go to the website from this link, and you can download the template, as well as instructions to specify data inputs for auditors to complete. So they really detail out how auditors are going to be completing their assessments based on the EU AI Act. And these are some of the deliverables: the model cards, the system maps, which we've talked about earlier as architecture diagrams and workflow diagrams, moments and sources of bias, testing of bias, and adversarial audits. So the model cards are short documents containing essential information about AI models, and they give you a template for building your model cards. They ensure organizations make informed decisions, streamline documentation, enhance transparency of AI models, which includes security controls. Next, we have a system map. The entire technology, the application integrates the AI model. So it's not just the AI model as well, it's also the application. We use the example of Oracle, human capital management, but there's Workday, there's Salesforce, there's ServiceNow, all have AI built into their systems. The user interface, the data pipelines. I'm assuming a lot of the people on these calls use one or more of those applications. So you should be able to go back and work with your application team to get a copy of their model cards. Maybe you'd have to do a non-disclosure agreement, but the point is you should be able to get a copy of their model cards. Moments and sources of bias. The AI audit establishes documents and tests to assess the compliance with legal and social requirements. Bias testing. Want to make sure testing is done on bias. This is related to the developers of the data. Different types of tests can be designed to determine whether bias. And then finally, adversarial audits are conducted to assess the effectiveness of the measures. The purpose is to ensure compliance with data protection. Some level of testing, evaluation, validation needs to be done. Red teaming or pen testing or threat modeling would be considered part of an adversarial audit. So that's really what I wanted to cover. I just want to leave with a takeaway, an action plan. I look at it 3 steps: develop a system security plan, conduct a control self-assessment, and then create the plan roadmap once you've done your self-assessment. Step 1 is form a team. Step 2, develop goals, objectives, deliverables. Step 3, identify those systems that are in the process of being implemented. Make sure you have a zero trust plan and program in place as well as an AI security plan. And again, I've labeled a few of these different control standards: NIST, Secure Software Development Framework; Google, Secure AI Framework; OWASP, et cetera, which we talked about briefly. We want to conduct a control self-assessment to protect the system, both in development and in deployment. Select the security tools and technology to protect those systems, again, in development and deployment. We assess the security current state of the controls as well as the target state, where we want to be. Identify the gaps between the current state and the target state, and put together a plan of action and milestones to mitigate the controls gaps, and a timeline and roles responsibilities for making sure we bring our current state up to the target state. And then finally, we want to create the program roadmap, establish a program improvement team, implementation time frame, assign resources, deliverables, metrics, implement the security controls, document the system plan, incorporate improvements from the initial assessment based on the system security plan, establish program playbooks for the technologies and the tools that you use to implement those security controls. Make sure you have playbooks that show how they work, and develop and implement controls monitoring, monthly KPI metrics. So that's really it.